Let's take a look at the Poisson distribution. Just an introduction, with an example. Example 1 says the amount of times that Josh makes a mistake on the board between 9 AM and 4 PM can be modelled using a Poisson distribution with a mean of 5. And then we're asked to find some probabilities. The first one says find the probability in one day, in other words between 9 and 4. Josh makes exactly 5 mistakes. So the first thing to realise about the Poisson distribution is this is the notation that we use. So like without this context, I could have just written down, we're looking at something that models a Poisson distribution, and the average rate is, the only thing that we need to know is like the average rate. So the average would be 5 in this time period. If the time period changes, then we'll have to change the average rate, but we'll see that a bit later. For now, we're just looking at between 9 and 4. On average, I would make 5. But if you think about it, like on every day, I'm not going to make exactly 5 mistakes. I might, some days I might make 4 mistakes, some days I might make 6 mistakes. But in general, if something can be modelled by a Poisson distribution, we're able to calculate the probabilities of different numbers of events happening within that time period. Okay. For the first example, I'm going to show you how to do it on the calculator, but then on the next example, we'll look at where this formula comes from and how we could use this formula. Obviously before the graphical calculators, we had to use these formulas to calculate the probabilities, and we also had to look them up in tables. But now we can just quickly do it on the calculator. Okay, so the way that we do this is we want to go on to menu 2 for statistics. And then we're going to press distribution. And then we need to scroll across with F6 because we're looking for Poisson. Okay, so we're working with the Poisson distribution. And then we get 3 options, PPD, PCD, and inverse P. We want it for this first example. We're calculating the probability of me making exactly 5 mistakes. So when we're getting a particular value, we press PPD because that gives us the exact value for one number of events. So exactly 5 or exactly 4, we can press F1. And then we enter the number in the question X, which is 5. Make sure data set's a variable. It should be on variable, never change that. Lambda, so the letter that we use, lambda, represents the mean. Okay, so in this question, I make an average of 5 mistakes per day. So both the value and the mean are 5 in this question. And then once you've entered those 2 numbers, you just press execute and the answer comes out. Okay, so we get 0.175467. And obviously, because we're working with decimals, I would recommend that we use 4 significant figures. So 0.175447, so 55. So 4, so. Okay, the next one, we're asked to calculate the probability that I make less than 5. So think about the number line, right? You could make it similar to the binomial list because we're working with discrete distribution. I could make 0 mistakes, I could make 1 mistake, I could make 2, I could make 3, I could make 4, I could make 5. The only difference between this one and the binomial really, or sorry, one of the main differences, is that like with the binomial you had a fixed number of trials, but I mean theoretically I could have like a really bad day and make a very large number of mistakes. Like there's no upper limit on the number of mistakes I would make. But the chance of that happening would be really small. So that our number line for this, the total number of mistakes could be anywhere between 0 and infinity. But we're being asked about less than 5 mistakes. So we can clearly see that as the same as less than or equal to 4. Okay. So we could calculate the probability to make 0 mistakes, 1, 2, 3, and 4, and I could add up all those probabilities using this formula. But the calculator will do that for us, like really quickly. And if we don't need to show the answer where it comes from, we can just state the value. So go back on to, distribution, scroll across, Poisson, but now we've got to press PCD. Okay, C stands for cumulative because we're adding up all these probabilities. If it was equal to a value, we press F1, but for everything else, when we're getting a range of values, we'll press PCD. Lower limit, so because we're going for less than 5, the lower limit would be 0. The upper limit would be 4. Don't include the 5 because it's got to be less than 5. And the value of lambda, the mean, the average number of mistakes, is still 5 in this question. Okay, so as long as we're on CD, we enter the values, press execute. I get 0.44049. Okay, the next one says greater than 3 mistakes. So think about the number line. What ones are more than 3, like greater than 3? Clearly we're looking for 4 or above, aren't we? Okay, but there is no upper limit. Okay, so like technically I could make it all the way up to like a really bad day, you know, infinite number of mistakes. One way of doing this in terms of like getting the method in the exam, like I'll show you 2 ways actually. So one way to do it would be set the lower limit could be 4, and then the upper limit just put like 1,000,000 in, like a really big number, and then that'll spit out the probability there. But like this, most people in the exam don't have a calculator will do this straight away for them. So let's show a little bit of method just to get the method mark. We know that the total of all of those probabilities will add up to 1. Like all of those events from no mistakes all the way up to infinite mistakes add up to 1. So if I wanted some way of getting more than 3 mistakes, which would be 4 or more, we could write the probability that x is greater than 3, the same as the probability that x is greater than or equal to 4, which is 1 minus, we know they all add up to 1. We want 4 or above, so we need to get rid of those ones. If we do less than or equal to 3, which would represent those probabilities, that's going to give us our method mark in the exam as well. So that if we want less than or equal to 3, we could set the lower limit to be 0, the upper limit to be 3. And that gives us 1 minus 0.265026, which would be 0.7349. 8, if I was going to round it, in other words, 0.7350. And you can check that's the same answer we got before by doing it the other way. Like you could set your lower to be 4 and your upper to be like a really big number, and we get 0.3497, which if we rounded that would be 50, wouldn't it? So it's the same answer. I'm just thinking about getting a method mark in the exam. I would prefer if we did it as a 1 minus calculation, because most people's calculators, or most people will look at the formula booklet and they would use less than or equal to for this one. Okay. Okay, so next one says between 2 and 5 mistakes inclusive. So if you think about this, if I want to include the 2 and the 5, between 2 and 5, we could write that as this. And our fancy calculator, to be perfectly honest, will give us this answer just straight away. But I'll show you the method in a second for what, if you look at mark schemes, the method will look slightly different than just the number that we write down. So our lower value would be 2, our upper would be 5, because we want between 2 and 5. And if you do want to press that, you will literally just spit the answer out. Oops, so it'd be 0.5755. But again, because this is like potentially maybe like a 3-mark question or a 2-mark question, we've not shown any method for that. So if you think about the way that most people in the exam will be doing this, because they use less than or equal to. If we wanted to swap between 2 and 5, we could do probabilities less than or equal to 5, which would give me all of those, and then minus. Can you see that if we want between 2 and 5, we'd have to subtract the 0 and 1. And this would be like a way of showing the method. And this is what the mark scheme would look like. So if we want less than or equal to 5, we'd go between 0 and 5, which would give me 0.61596. Less than or equal to 1, we go from 0 to 1. That'd be 0.040428. Okay, and if we do that subtraction, we get 0.575532, which is the same as what our calculator just spit out, just from using between 2 and 5. Okay. Depending on what the question asks, like if it's a show question, you need to show some working out. If it just says find the value, you can just write the value down and you'll get the marks. Okay. The next example I'm going to show you is where we've actually, because it could be asked as a show question, so we need to look at like how we could actually use this formula. Okay, so example 2, we've got a show that question, and we've just got to be careful of this because obviously most of the questions that we're going to be doing will be on the calculator. But if we do get a show question, like just look at, what someone might do. Go on to menu stats. We're working with the Poisson distribution. And this one has got an average, so we know that lambda is equal to 4. So whatever this question is, we're looking at an average rate of 4 within that time period. If we go on to distribution Poisson, so exactly equal to, we press F1. 3, lambda, average of 4. That spits the answer out, but you've not shown it, have you? Like you can't just go, oh, I did press the buttons on the calculator, that's the answer. Okay, if we are asked to show it, we need to think about this formula here. Because this is where the actual value, like our calculator is using this to tell us what these answers are. Okay, so the probability that x would be equal to 3 is e to the minus lambda. Now in this question, lambda is equal to 4. Lambda, which is 4, to the power of x. So the specific value in the question, x is equal to 3. All divided by x factorial, which would be 3 factorial. So if we go back onto the normal maths option, and we enter e, which is shift e, to the power minus 4, and then times that by 4 cubed, and then divide that by 3 factorial, which is 1 times 2 times 3, which is 6. I'd get 0.1953668. And by writing this formula down, we've shown where the answer comes from. And another good idea as well is to give you the answer, write it more accurate and then round it afterwards. Because if you write it more accurate, it's more evidence that you've not just like written the number down that they've given to you in the question. Okay. One thing that I haven't really mentioned is this E. Maybe you've not seen that yet in maths, but we'll see a lot of that in maths sort of towards the end of this year. E is just a number, which is like 2.718. 281. It's a bit like pi. It's one of those special numbers in maths that we will learn about a lot, but for now I'm not going to go into it. Like it's just a number that we can press on our calculator, which is, see where this ln button is. If you press shift ln, that's where this e is. Okay. So for the last one, we want to show that the probability of it being less than or equal to 2 is equal to this. So if we want it less than or equal to 2, again, we've got to show where the answer comes from, so we're not just going to go to the distribution on the calculator. Less than or equal to 2 would be the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2. So if I wanted to show where this comes from, because that's what I'm being asked, it'd be e to the minus lambda, which would be minus 4. Lambda, which would be 4 to the power of x, which would be 0, divided by 0 factorial, plus e to the minus 4, 4 to the power 1, divided by 1 factorial, and then e to the minus 4, 4 squared, divided by 2 factorial. Another thing that I'm not going to go into now, but 0 factorial is equal to 1, okay? So just trust me on that one. So what we would get, if we were working these out, so for this one, 0 factorial is 1, 4 to the power 0 is 1, so that would be e to the minus 4. Let me just work out these other ones. Okay, so I calculated each of these and added them up, and we got 0.23810, which is showing where the answers come from. Okay, notice as well that these numbers, like if something does model a Poisson distribution, so you'd expect it to be 4. So say if you think about me making mistakes, if you expect me to make 4 mistakes in a day, the chance of me not making any is really small, like if this does accurately follow a Poisson distribution. And notice that the chance of me making 1 is a little bit larger, the chance of making me 2, it's about 15% chance of me making 2 mistakes. Chance of me making 3 mistakes is around about 20%. And like that, you should try and get a feel for the numbers as well as just calculating them. Like if you expect 4 to happen, the numbers around 4, there'd be a good chance that that happens. If I said what's the chance of me making 20 mistakes, the chance of me making 20 mistakes would be really low if this was going to be modelled by a Poisson distribution. Alright guys, thank you.